Okay, so one thing which I want to talk about for a very long time was quantum spin, and how it's grossly misunderstood. So, whenever we talk about spin, especially in the case of fermions like electrons, we talk about spin half, and people think it's some charged ball which is moving around its own axis, which causes the angular momentum. Well, that's classical angular momentum, and it couldn't be more wrong. And it's so frustrating to see that people just, because they haven't been taught the way spin actually works, it's like a, it's like the most, like I would say it's the most common misunderstanding present in physics. So the problem is, electrons don't actually spin like this. Why do they not spin like that? Because if we measure the angular momentum which we talk is generated by that spin, the electron needs to spin faster than the speed of light, so which violates a lot of physics principles, and that's why they actually aren't rotating like this. What spin actually is that there is an intrinsic amount of angular momentum inside these particles. And what do I mean by intrinsic amount of angular momentum? Well, to understand that, we need to first talk about something called spinors. Now, this is I love spinors because I've been working on them for like a year, and they're wonderful mathematical objects. So spinors are these weird mathematical objects like vectors, where a 360 rotation won't bring them back to its original configuration, but a 720-degree rotation will. So if I take, let's say, this bottle, and if my hand has to come back to the same rotation after spinning it, if I turn it by 360, my hand is now, not in the same position as it was. So I turn it once more, and then it comes back to its original position. So this was 360 and 360 again, that gives us 720. So if I turn it like this, it is 360, and now once more, that's 720. So this was a very crude example of, but it still tells us that spinors have a rotation of 4 pi and not of 2 pi. So that is what we call a spinor. Now, if we talk about how we relate this to electrons, when we say spin half, we mean that in our space, this rotation, okay, so when we turn it 720, it looks two rotations in our space, but in the spinor space, it's just one rotation. So when an electron moves, through 360 degrees in our space, it's moving just by half a spin in its spinor space. But that's just complicated mathematics. Let's talk about why these spinors came to be. So, we all know what's the Heisenberg uncertainty principle, that the more you know about the momentum, the less you know about the position, and where linear momentum delta p and position x are conjugate variables. So, according to Noether's theorem, these laws were derived because of Noether's theorem of symmetry. According to Noether's theorem of symmetry, uh, when you have translational change, that is basically position, and you have a change in the momentum, that leads to the conservation of momentum. So again, let's just think about it. Basically, Noether's theorem talks about the symmetry between conservation laws and invariance in space. So translational invariance, when you change stuff, when you change coordinates, leads to the conservation of linear momentum. So if you change angles, it would lead to the conservation of angular momentum, and that is the reason how we get the other conjugate pair, which was seldom talked about. In Heisenberg's pair, you have linear momentum p and you have position delta x. Now, if we were to change linear momentum to angular momentum, you get angular position, and that is where the whole concept of spinors comes in, the angles 360, 720, and all that. Now, there's one very interesting thing about spinors and how we know that electrons behave as spinors is that all fermions do, is that when Paul Dirac was working with the Schrodinger equation, to make it work, he had to use spinors instead of vectors. With vectors, it just didn't make sense because it would give you minus signs. Because when you turn by 360, it is giving you the opposite of what's the actual like the initial orientation. So there you get a minus sign because the wave functions are antisymmetric. But to fix that, when you used spinors, what happened was you get 2 degrees of rotational freedom in the equation. So what happens is, let's say you have a wave moving through space. If I shift, let's say you have 2 waves. If I shift the waves by by 1/2, let's say half of a cycle, they cancel out, right? Because it will be destructive interference and they nullify to 0. Now, if you can think of it in terms of rotation, let's say if I rotate it and it's not coming back, let's say in phase, it's going 1/2 cycle out of phase, that will cancel it. So that is what happens with quantum spin with fermions, that if you rotate it by 360, it's sort of as moving it 1/2 cycle out of phase and cancels it. And that's what spin represents. So this was a very brief video on how to get an intuition about how spin actually works. So just spinors, which is the bottle trick where you have to turn your hand 720. The conjugate variables being instead of p and x, it'll become L and theta, because it'll become angle and angular momentum. And electrons don't actually move around like balls. They are not charged balls spinning around faster than the speed of light. So frankly, nobody understands spin. We just know the mathematics behind spin. So yeah, that's about it. Thank you for watching.